When you lie down at night and the world begins to soften, there's a moment when your body sinks just slightly into the bed. The mattress welcomes your shape, and the blanket resting on your chest feels heavier than it did during the day. Not too heavy, just enough to remind you of where you are. That pressure, that gentle press. What is it exactly? Is it the blanket that's heavy, or is it you who gives it weight in return? We call it comfort, but comfort has a texture, and sometimes it feels like the world is whispering down through your bones, saying you belong right here, unmoving. That whisper, soft as it may be, has a name in science: mass. But when we say something has mass, what do we mean? Is it just how heavy something feels when we try to lift it? The heaviness of a box when we carry it up the stairs? Or the resistance we feel when trying to push a stubborn drawer back into place? We use the word so easily, as if it were simple, but the truth is, it's not. Mass is one of those strange ideas we use every day without ever truly touching it. Let's begin with that feeling under your blanket. It's easy to say you feel your own weight pressing into the bed, but weight depends on gravity. If gravity were to vanish, even for a blink, would your mass disappear too? If you floated weightlessly in space, would you still be you? Would your body still resist motion, still be reluctant to change direction? Consider this. Astronauts in orbit are weightless, yet they don't lose mass. If one astronaut nudges another, both drift apart, slowly, but with a definite rhythm. Their bodies resist being moved, resist being sped up, even though they don't feel heavy. That resistance, silent, invisible, is the signature of mass. It's not about how hard gravity pulls you. It's about how much you resist when something tries to change your motion. But where does that resistance come from? Is it packed inside the atoms that make up your skin, your muscles, your bones? And if so, where inside the atom does mass hide? After all, an atom is mostly empty space. Electrons whiz around, but they're nearly massless. The nucleus holds most of the mass, but it's just a speck in a vast sea of emptiness. How can almost nothing add up to something so solid? Now picture something familiar. You're standing in a grocery store, gently pushing a shopping cart. One wheel is jammed and it resists you. You apply force, it doesn't glide. It fights back, stubborn. Now imagine you're pushing an identical looking cart, but this one is packed with water bottles. It resists too, but differently. Not because of a broken wheel, but because of the sheer amount of stuff inside. You feel its mass in the way it refuses to speed up. That refusal is not noisy. It doesn't yell. It just calmly says, "It takes more to move me." So is that what mass is? Just stuff? More particles inside an object? It seems to make sense, until you realize how little of an object's mass actually comes from the mass of its parts. A proton is made of quarks, yes, but the quarks themselves contribute only a tiny fraction to the proton's mass. Most of it comes from something else, something subtler, the energy of motion, the binding between particles, the dance of fields. Imagine a pot of boiling water. You can't see the heat, but you feel it in the steam, in the way the bubbles rise. That motion is invisible, yet it shapes your experience. In the same way, mass might be the echo of motion at a level far beneath what our senses can detect. We like to think of mass as a thing, something you can hold or count, but it's more like a property, a behavior. a kind of hush that wraps itself around particles, slowing them just enough to be part of the world we know. When you push a wall and it doesn't move, it's not just the wall refusing, it's mass, quietly standing its ground. Now drift your mind to the moon. Lighter gravity, smaller weight. You could jump higher, feel freer, but your mass stays the same. Your bones, your muscles, they resist motion just as much. It's only gravity that's changed, so weight depends on where you are. But mass stays with you. Even in the dark, even in stillness, your mass is there. It anchors you, defines you, gives you substance in a world made mostly of emptiness. It's not loud, it doesn't shine, but it's what makes you real, and somehow it also makes the universe obey. Because mass doesn't just resist, it bends. It curves space, tells time how to tick, tells planets how to orbit. But how? How can something so passive, so silent, reach out and shape the geometry of space itself? Maybe mass is more than what's inside you. Maybe it's a relationship between you and the space you occupy, between the energy you hold and the way the universe wraps itself around that energy. Maybe it's not just what you are, but how you are allowed to move, how you resist, how you stay. And if we trace that thought further, we arrive at a strange possibility that mass is not something we possess, but something that is granted by space, by fields, by motion, by a universe that has rules, and resistance is one of them. So when you lie still beneath the weight of your blanket and feel the pull of the earth, maybe that pull is a quiet reminder of your mass, of the silent force that makes you harder to move. Not because you're stubborn, but because you are deeply, fully there. And if the force that makes you feel heavy disappeared, gravity, the earth, the bed itself, what would remain? Imagine that gravity vanished just for a moment. Not a violent snap, but a soft lifting, like someone gently undoing the strings of a marionette. No weight, no tension. The blanket on your chest would no longer press down. It would float like a mist, neither falling nor rising. You would drift, body and breath unanchored. But something curious would still be there. If you tried to push off from a wall, you'd still feel resistance. Your arms would strain, your body would react slowly. Even without gravity, you would still be hard to move. That lingering resistance, unchanged by the absence of weight, is mass. Now picture yourself stepping onto the surface of the moon. You take a step, and suddenly you're higher than expected, suspended just a little longer in the air. You're not flying, but your feet spend more time off the ground. Your body feels light, like a dream version of yourself. Yet if someone were to throw you a toolkit, one they used on Earth, it would still require effort to stop it. You'd catch it with both hands, feeling its mass tugging at you, even though its weight has diminished. It's still hard to stop, hard to start, hard to turn. On Earth or the moon, that quality doesn't change. What is it that stays constant? Mass does. Not the heaviness that ties you to the ground, but the slowness with which your body responds to change. The moon lets you leap, but it doesn't make you easier to accelerate. Your body's reluctance to change direction is a kind of memory, etched deep into its fabric. It doesn't matter whether you're on Earth, on the moon, or drifting silently through space. That resistance remains. It is intrinsic. So then, what exactly is this intrinsic thing? Where is it located? If you could peel back the layers of your body, skin, muscle, cell, atom, Where would you find mass hiding? Let's go deeper. Each atom in your body is made mostly of empty space. Inside, a tiny nucleus is orbited by electrons whizzing at high speeds. Those electrons have almost no mass at all. The nucleus contains protons and neutrons, which make up the bulk of the atom's mass. But even those are made of smaller things, quarks. And here's the surprise. Quarks are incredibly light. The combined mass of all the quarks in a proton accounts for only a tiny percentage of the proton's mass. So where does the rest come from? It's not a trick question. It's not hiding in the particles. It comes from the energy that binds them. The motion, the tension, the activity inside, those swirling, churning, glimmering interactions. It's as if the very effort of staying together, of being bound into something, creates weight. The proton has mass not because of what it is, but because of what it does, because of how it moves. That means mass isn't just about stuff. It's not the bricks in a house. It's the blueprint, the forces, the tension in the beams, the wind trying to push it over and failing. It's the dance, not the dancer. Imagine holding two suitcases. One is filled with bricks, heavy as expected. The other looks identical, but it's filled with trapped springs, tightly compressed. It feels just as heavy, even though it's full of tension rather than material. Which one has more mass? Both. Because mass doesn't care how you store your energy, only that it's there. Compressed springs, swirling particles, bound fields, they all count. And now, let your mind drift to space again. Imagine two satellites, alike in size, floating near one another. One is filled with ordinary metal, the other is hollow, but spinning internally, small rotors whirling within. They look the same from outside, but if you try to push them, one resists more. Not because of weight, but because of mass. Because energy has mass. The spinning rotors store kinetic energy, and the satellite holds it like a memory. A mass that wasn't there before now exists, not from added particles, but from motion itself. Energy and mass are tied, fused, inseparable. Einstein whispered it to the world with the quiet power of a single equation. Not just energy equals mass times speed squared, but something deeper. Mass is a form of energy. One becomes the other, depending on how you ask. If you could compress light, pure, massless light, into a small enough space, it could collapse into a black hole. Weightless things can gain mass if they are concentrated enough. Which brings us to another thought. If energy and mass are intertwined, does that mean you can make mass out of nothing but movement? Could a field of motion become a thing? That's what happens inside every proton. Quarks race around and bind together, and that effort becomes substance. Not imagined, not metaphorical, measurable, tangible mass. And yet, even this understanding raises more questions. If mass is the result of energy, why do some particles have more than others? An electron is thousands of times lighter than a proton. Why? Why does a top quark weigh as much as an entire atom of gold, while a photon, full of energy, has no rest mass at all? Could there be something else at work? Some field or mechanism that grants mass to particles, depending on how they move through it? Maybe mass is not just a consequence of motion, but of how motion is allowed, of how particles interact with the stage they move across. Like a dancer pushing against the floor, some floors are sticky, some are smooth. Could there be an invisible floor to the universe, one that decides how hard it is to move, how heavy things feel. The idea seems strange, even poetic, but perhaps it's not poetry, it's physics. And if the feeling of weight on your chest is only part of the story, if the deeper truth lies in the way you resist being moved, then maybe mass is not just something you carry, but something that responds to you, something that says, "You're here, you exist, you take effort to move, you matter." And that gentle pressure you feel as you lie in the dark, perhaps it isn't just your body settling into the mattress. Maybe it's the quiet voice of the universe, reminding you that presence takes effort, that being isn't effortless. But what if there is something even deeper than that? Something that gives even the tiniest particle its sense of resistance, its refusal to be moved too easily. Picture a dancer stepping onto an invisible stage. She moves effortlessly at first, sliding through space like light. But then something subtle begins to pull at her limbs. Not gravity, not friction, but a kind of drag that only appears when she tries to move. It's not a wall, not a barrier, just a thickening of the air, a softness that tugs back. She can still dance, but every gesture takes effort. Every twirl is slightly muted. She's moving through something unseen. And strangely, this invisible resistance gives her shape, weight, substance. That's the image physicists use when they describe the Higgs field. The Higgs field is not like air or fog. It doesn't swirl or stir. It's constant, uniform, everywhere. Every particle moves through it, but only some feel its presence, some glide as if nothing were there. Photons, for instance, pass through untouched. Others, like electrons and quarks, experience a gentle resistance. The more they interact with this field, the more they seem to gain mass. Not because something is added to them, but because something slows them. Like syrup thickening around a spoon. The particles aren't growing heavier by swallowing something. They're simply being held back, subtly, consistently. It's a strange idea that mass could arise from interaction, that it's not a built-in property, but a response to the world, that a particle becomes massive, not because of what it contains, but because of how it moves through something else. This shifts the whole question. We stop asking, what is mass made of? And instead ask, what slows you down? When physicists finally discovered the Higgs boson in 2012, it wasn't because they saw the field itself. You can't see the field. You can only see what happens when you excite it, poke it, ripple it, momentarily disturb its smoothness. That ripple is the Higgs boson. It flickers into existence for a moment and then vanishes like a single drop rising from a still lake. But in that flicker is proof. The field is there. It has always been there. Everything we call matter has been moving through it, slowly or quickly, depending on how strongly it interacts. But this opens yet another door. If mass comes from the Higgs field, then where did the Higgs field come from? Why does it exist? Why does it fill all of space? And why do different particles interact with it differently? The electron and the top quark are both fundamental particles, yet one is feather light and the other is heavy like lead. What decides how much resistance each one feels? No one knows. The field is constant, but the way particles respond to it, that part remains a mystery. Perhaps it's like personalities walking through fog. Some barely notice it. Others find their clothes soaked instantly. It's not the fog that changes. It's how each traveler responds. But what makes them different? What's written into their nature that determines their path through the Higgs field? These are the kinds of questions that don't have answers, only clues, and so we find ourselves circling back. Mass isn't a single idea, it's a convergence. Part of it comes from energy, from the dance of particles and the tension that holds them together. Part of it comes from fields, from invisible resistance woven into the structure of the universe. And maybe part of it comes from something deeper still, a symmetry that once existed and then broke. In the earliest moments of the universe, everything was uniform. No masses, no separations, no particles with personalities. Just energy, fields, motion. Then, like the soft cracking of ice beneath your feet, the symmetry broke. Some particles stayed massless. Others began to slow, to feel resistance, to gain weight in a world that no longer treated everyone equally. The universe cooled, structure emerged, and suddenly matter existed. That broken symmetry is not just a detail, it is the turning point. Without it, the universe would be full of light, but empty of form. There would be no stars, no planets, no cells, no bodies beneath warm blankets. Symmetry had to shatter for mass to appear, and because of that, you are here. But that means mass is, in some sense, a record of the universe's first imbalance. A memory of a change so subtle and yet so consequential that it echoes in every particle, in every step you take. The resistance you feel when lifting your arm, the weight of your footsteps, the way your body settles into the earth, all of it comes from that ancient rupture. And still, this answer feels incomplete. If mass is the product of resistance, of interaction, of broken symmetry, why does it feel so real? Why does it still seem like a thing, a possession, something you carry around in your body like luggage? Why does your body settle into the bed, drawing the blanket close, if it's all just interaction and tension? Maybe it's because we live in a world shaped by these patterns, and our senses are tuned to the outcomes, not the origins. We don't feel the field, we feel its consequences. We don't perceive the break in symmetry, we perceive the shape it leaves behind. Mass feels solid because we are solid. We are the results of these invisible rules, and perhaps that's why the universe can be so baffling. It's not trying to explain itself to us. It's simply allowing us to exist. Now imagine, again, that dancer on her invisible stage. She tries to leap, but the stage holds her back, just a little. Her arms slice through resistance that isn't air. Her movements are slowed, but also made real. Without the field, she would be a blur, a streak of light. With it, she becomes a figure, a form, a mass. So when you lie still at night and the world around you fades, remember that you are not floating in emptiness. You are resting in a quiet sea of resistance, a field that grants substance to your breath, to your bones, to your heartbeat. You do not simply have mass. You are mass responding gently to a universe that shaped you through its own stillness and resistance. And yet, for all we've uncovered, could there be particles that carry no mass at all, yet still move, still touch, still change the world? Think of light. It travels endlessly, effortlessly, never stopping, never resting. You can't weigh a beam of sunlight. Try to trap it in your hand, and it slips through like a dream. And yet, it warms your skin, it powers the leaves, it moves satellites. Light, though massless, carries energy. It has momentum, It can nudge particles, create pressure, even leave behind trails of change. How does something that weighs nothing push the world? Photons, the particles of light, have no rest mass. They never stop moving. They can't. To be still would mean not to exist. And yet, they are not powerless. When they strike a surface, they exert a gentle pressure. It's small, too small for your hand to notice. But in space, where there's no air, light alone can propel a spacecraft with sails no thicker than paper. The photon, though massless, leaves an imprint wherever it passes. So, what does this tell us about mass? It tells us that mass is not the only way to be real, not the only way to have influence. Energy moves through space in many forms. Mass is one, motion is another. Photons remind us that even the lightest thing, literally weightless, can have presence, can affect, can carry force. But still, they are different from us. They cannot rest. They cannot be still. To lack mass is to be condemned to speed, always moving, always at the limit. There's no halfway, no pause, no contemplation, only forward, always. Now let's turn back to those things that do rest: a rock, a chair, your own body. You can sit still. You can exist without moving. You can store energy in place. That ability to be without motion is tied to mass. It's what separates a photon from a proton. A massless thing has no rest. A massive thing has the option. Einstein's great insight, spoken in the quiet symmetry of energy, equals mass times the speed of light squared reveals something profound. Mass is energy in a different form. The energy of stillness, the stored potential of being. If you could convert all the mass in a small coin, say a single gram, into energy, you would unleash more power than a major bomb. That's not metaphor. It's measurable, tested, real. Mass is not dead weight. It's a reservoir. And this connection goes both ways. You can convert energy into mass. In high-energy particle collisions, like those in powerful accelerators, bursts of kinetic energy turn into new particles with mass. Where there was once only motion, now there is substance. It's like stirring a pot so fast that ingredients form from the motion itself. The universe allows such trade-offs as long as the rules are obeyed. But these exchanges, however elegant, lead us to stranger territory. If energy can become mass, and mass is just stored energy, then what determines the form? Why does one energy burst become an electron and another a muon or a quark? The universe seems to have a kind of menu, and when energy reaches certain thresholds, it selects from that menu. The patterns are consistent, but the reason behind the choices remains unknown. Maybe mass is not just about storage, or resistance, or interaction. Maybe it's also about identity, a kind of fingerprint for how a particle lives in space, how it dances with the fields around it. Two particles might have the same charge, the same spin, but different masses. Why? We don't know. But they act differently, move differently, age differently. Their mass gives them their pace, their rhythm. This brings us to the odd realization that mass isn't just a property. It's a boundary, a rule book. It defines what a thing can and cannot do. A photon will never rest. An electron will never reach the speed of light. Their masses are not merely weights, they are permissions. Permissions encoded by the universe into the very fabric of what things are. And it gets stranger still. When you bring mass and energy together into one equation, one language, you also bring space and time into the mix. Because mass bends space, It slows time. It creates gravity. The more mass an object has, the more it distorts the spacetime around it. You feel this distortion as weight, but it's deeper than that. It's a warping of the very stage on which the universe unfolds. You don't fall toward the Earth because it pulls you. You fall because the space around Earth is curved. You are following the straightest path possible through a warped geometry. Mass bends that geometry. And the more mass, the more the bend. So mass doesn't just sit there, it shapes reality. It molds the flow of time and the curves of space. And yet, it remains silent. You can't see it. You only see its effects, the way things fall, the way time slows near a massive star, the way light bends when it passes near a planet. And that quiet influence raises a question. Is mass truly something that belongs to particles? Or is it something that emerges from their relationship with space, with motion, with time? Perhaps it's like tension in a rope, not located at any one point, but existing only because of the pull between ends. Maybe mass is not a thing, but a condition, a state that emerges when energy, space, and interaction meet in just the right way. That would explain why it's so hard to define, why it feels so real and yet always just beyond our grasp. And so, lying here, still beneath your blanket, you are not simply carrying your mass like a burden. You are embodying it. You are an energy, paused, a presence that warps the space around you, that slows time ever so slightly. You are not only moving through the universe, you are shaping it gently with your mass. But then we wonder, if the atom is mostly empty and the particles inside are nearly massless, and mass itself arises from motion, tension, interaction, how can something so insubstantial create the solidity we feel in the world? Close your eyes and picture your hand resting gently on the mattress. You press your fingers together and feel the firm resistance of your own skin. Tap the bed frame and hear a dull, confident thud. Knock on a wooden table and your knuckles push back with a solid reply. Everything feels solid, grounded, undeniably real. And yet, beneath that sense of firmness lies a strange truth. Everything you're touching is mostly empty space. The atoms that make up the bed, the table, your own body. Each one is a vast, silent landscape of nothing, with tiny flickers of matter dancing across it. The nucleus, where most of the atom's mass resides, is a speck at the center. Electrons orbit far away, like moons around invisible planets. So how can so much nothing feel so full? The answer, it turns out, has little to do with mass itself and everything to do with forces. When your hand touches the table, it doesn't fall through because the electrons in the atoms of your hand are repelled by the electrons in the table. Electromagnetic forces, acting invisibly, push back. They create the illusion of touch, the sensation of hardness. So you're never actually making contact at the atomic level. You're hovering near, held apart by a quiet standoff. And yet it feels completely solid. So we must ask, if mass isn't what makes things feel solid, then what does it do? Mass gives objects their inertia, their reluctance to be moved, sped up, or slowed down. It's not what makes a wall unbreakable. It's what makes it resist acceleration when you try to shove it. It's a quiet defiance, not a loud strength. And on the tiniest scales, it's a dance. Quarks, trapped inside protons and neutrons, move at astonishing speeds, bound tightly by the strong nuclear force. Their motion, their energy, their binding, That's where most of the proton's mass comes from. The parts themselves, the quarks, are almost massless, but their effort to stay together creates a kind of tension, and that tension is mass. It's as though a house were made of string, but the way those strings pull against each other gives the house structure, shape, weight. The mass isn't in the pieces, it's in the struggle to stay whole. Energy, in the form of binding, creates something we interpret as mass. And this is not just poetic thinking, it's measurable. In experiments, when you break apart nuclei, the energy released reveals that the whole weighed more than the sum of its parts. That extra weight, the binding energy, was quietly adding mass all along. But this introduces a strange shift in perspective. If mass comes from energy, and energy comes from motion, or fields, or binding, then mass is not an ingredient. It's a result. It's not poured into particles, like syrup into jars. It emerges from what those particles are doing, how they're held, how they spin, how they connect. Mass is not a thing. It's a consequence, and it gets even stranger. If you could somehow remove the motion, the binding, the fields, if you could freeze the internal energy of a proton to absolute stillness, its mass would nearly vanish. Not completely, because a sliver of mass comes from the tiny mass of the quarks themselves, but most of it would simply disappear. Not because something has been taken away, but because something has been unmade. The activity that was mass would simply no longer be happening. And so mass becomes a kind of story, a narrative told by fields and motion, tension, and balance. A thing is not heavy because of what it contains, but because of how intensely it holds together, how much energy it needs to remain itself. Mass is persistence, expressed in terms of resistance. A story of no, I will not be moved, whispered over and over at every level of structure. Still, the solidness of things, the firmness you feel when you grip a doorknob or sit on a wooden chair, tempts you back to simpler thinking. We feel mass as weight. We experience it as presence. But now you know that this presence is the ghost of motion, the echo of forces, the signature of tension made physical. And if we follow this thread further, we begin to wonder about stillness. Can anything ever truly be still? If mass emerges from motion and binding and activity, then perhaps stillness is not the absence of movement, but the perfect balance of it. A kind of harmony where movement continues inwardly, but with such precision that it seems like rest. Your body, lying quietly in bed, appears motionless. But inside you, trillions of atoms vibrate, molecules collide, quarks swirl. The very fact that you are requires motion. Even your mass is a record of that motion, its trace, its leftover weight. And when we speak of weight, we're already back to gravity. Mass bends space, curves time. The energy trapped in particles, the forces binding them, those things distort the very geometry of the universe. That's why planets orbit stars, and why your feet feel anchored to the ground. But the curvature of space caused by mass isn't sharp or sudden. It's gentle, diffuse, more like the soft depression your body makes in a memory foam mattress than a hole in the ground. Mass doesn't tug, it invites. It tells the space around it, come closer, bend gently, and space listens. Objects that enter this curvature follow its lines, not because they're pulled, but because they're moving straight in a space that's no longer straight. That's gravity, seen not as a force, but as a conversation between mass and space, So when you walk across the floor, or lie still beneath your blanket, or toss a pillow into the air and watch it fall, you're watching these conversations unfold. The pillow curves along the invisible slope your body makes in spacetime. Your mass talks to the planet's mass, and the ground rises to meet you. Every movement, every fall is a reply, and that reply depends on your mass, not your size, not your volume, but the sum of your persistence, your stored energy, your internal motion. Even when you sleep, even when you dream, that quiet resistance is still there. But it leads to a new question. If mass emerges from energy, from motion, from fields and forces, then what is the origin of those fields? Where do they come from? What lays the groundwork for this hidden dance? Try to imagine space not as emptiness, not as a void, but as something with substance, not like air or mist, but more like a field spread out across the entire cosmos. A field that doesn't sway or shimmer, but rests there invisibly, humming gently beneath all matter, even when nothing moves. This field, and others like it, are what lie underneath mass, underneath the particles themselves. Quantum fields, those silent, pervasive fabrics, are the true building blocks of reality. Every particle is a ripple, a brief disturbance in one of these fields. Electrons are ripples in the electron field. Quarks are excitations in their own fields. And somewhere, deeper still, those fields are defined not by objects, but by rules, by symmetries, by the ways they are allowed to vibrate. Even when nothing is happening, no light, no movement, no noise, the fields are still there, not flat, not truly empty. They simmer with potential. This is the vacuum of space, and it is not a vacuum in the way we once imagined. It is not zero. It is not absence. It is a sea of possibility, thick with flickering fluctuations. Virtual particles appear and vanish before they can be named. They don't stay. They don't last. But they leave behind traces, tiny nudges, ghostly effects, measurable shifts. This restless nothingness is where the Higgs field also lives. It is not the only field, but it is a special one, uniform, invisible, omnipresent. Without it, particles would have no mass. They would move endlessly, unstoppably, without ever slowing down. But with it, something changes. As particles move through the Higgs field, they resist. They acquire inertia. They acquire mass. The field doesn't push or pull. It gently slows. It changes the nature of motion, and the way it couples with each particle is specific, like a fingerprint. Some particles barely feel it. Others are soaked in it. That coupling, that invisible bond, defines how heavy a particle will be. But why do particles couple differently? What sets the strength of their interaction with the Higgs field? No one knows. The electron, so light, barely interacts. The top quark, heavy like a gold atom, clings to the field with a much stronger embrace. The field itself doesn't vary. It's constant. So the variation must lie within the particles. But what in them could decide such a thing? We don't have that answer yet. All we know is the pattern, the behavior, not the reason. It's like watching dancers cross the same floor, but some glide while others drag. The floor is smooth and unmoving. So what makes the difference? The shoes, the posture, something within the dancer we cannot yet see. And yet, despite this mystery, we can measure the results. We know the masses of particles, down to extraordinary precision. We know how they behave. We know how they decay, how they move, how they resist acceleration. We know the script, But the origin of the scriptwriter remains hidden, and still the vacuum murmurs beneath it all, a place that isn't empty but full of structure. The vacuum holds energy, not a metaphorical energy, but real, measurable energy that has physical effects. It bends space, it influences motion, it might even explain the acceleration of the universe itself. There is a strange symmetry in this idea that mass, which feels like solidity, permanence, and presence, might actually arise from something as abstract and shapeless as a field in a vacuum. That's something we equate with the heaviness of the body, the clunk of a hammer, the anchor of gravity, might originate in a field that can't be touched, only inferred. And if mass comes from fields, and fields are everywhere, then perhaps everything is built from nothing but disturbance, tiny movements in an invisible ocean. We are not made of things, but of excitations. We are not built from marbles and bricks, but from notes in a symphony of fields. Even our mass, the thing we think of as weight, as substance, is nothing more than a sustained ripple, a ripple that won't fade because the universe has allowed it to keep singing. But this brings up another twist. If particles get mass from the Higgs field, why do some massless particles, like photons, still affect the world? How can something with no mass still have energy, still carry force, still light up the sky? The answer lies in motion. Photons never stop. They are always moving at the speed of light, always racing along the threads of space, never slowing down. Because of that constant motion, they can carry energy. They can exert force. They can heat your skin, power a solar panel, knock electrons loose from atoms. Even without mass, they matter. Their energy gives them momentum, and in this way, they shape the universe without ever resting in it. Massless particles live on the edge. They are forever in motion, and their influence is tied to that speed. Massive particles, on the other hand, have the luxury of pause. They can rest, they can gather, they can form structures. Mass allows the possibility of stillness, of being in place. That difference, motion versus rest, is fundamental. It means mass is more than resistance. It is a condition for complexity. Without mass, the universe would be a blur of light and energy, rushing past itself with no time to form stars, planets, or thought. Mass gives time a place to slow down. It lets atoms form, molecules dance, life breathe. You, lying still in your room, are a monument to that slowness, not inaction, but possibility. The fact that you can stop, rest, think, sleep, that is mass at work. That is the Higgs field holding you gently, allowing you to exist in a form that doesn't dissolve into speed. And yet, if all this is true, if the vacuum is full, if fields are real, if mass is just a ripple in the quiet, then what lies beneath that ripple? What is the structure that holds the fields themselves? What gives space the ability to support these invisible patterns? Beneath the fields, beneath the quiet fluctuations and ripples that we call particles, there lies something more abstract, something harder to name: space itself. Not the kind of space you can enter or cross, but a mathematical stage, an invisible framework on which all the fields are written. This space isn't empty. It doesn't sit still. It's defined by possibility, by symmetry, by the allowed ways that fields can vibrate, interact, twist, and bend. When we ask what gives structure to the Higgs field, or the electron field, or the quark field, We are asking about the rules of space itself, about why the universe allows some things and forbids others. Symmetry is at the heart of this structure. In physics, symmetry doesn't mean visual balance or pretty patterns. It means that something remains unchanged when you perform certain transformations. Rotate the system, shift it in time, flip its charge. If the laws stay the same, there's symmetry. These symmetries are not aesthetic. They are powerful, foundational. They give rise to conservation laws. The symmetry of time implies conservation of energy. The symmetry of space implies conservation of momentum. The universe runs on these hidden balances. But here's the curious thing. For mass to exist, some of these symmetries must break. If the Higgs field were completely symmetrical, every particle would interact with it in the same way. Or not at all. But it's not. The symmetry is broken, not shattered, but softly tilted. That tilt is what allows particles to acquire different masses. The universe, once perfectly even, developed imperfections. Not randomly, but purposefully. These imperfections gave rise to structure, to mass, to difference. They let the early universe evolve into what we now see. It's a bit like watching a calm pond freeze. At first, the surface is uniform, smooth, symmetrical. Then, as it cools, tiny cracks appear, then grow into patterns, frost, branches, lacework. The original symmetry is broken, and beauty emerges. In the same way, the early universe cooled and broke its own symmetry, and out of that, mass appeared. This idea that structure emerges from broken symmetry is strange but essential. It means mass is not just a property, but a memory, a trace of a time when the universe changed direction, a fossil of a moment when stillness gave way to form. And it means the vacuum itself, the lowest possible energy state, is not truly featureless. It holds structure, decisions, history. In quantum field theory, even a vacuum is active. Particles flicker into and out of existence, not violating any laws, but allowed by the rules of uncertainty. These virtual particles exist for brief moments, influencing nearby particles, shaping outcomes. Their contributions are subtle, but essential. Without them, our predictions wouldn't match reality. The vacuum is a place of quiet unrest. Even more curiously, this vacuum energy is not zero. It has a value, one we don't fully understand, and this energy adds up. Over vast distances, it creates a pressure that pushes space itself outward. This may be the source of the universe's accelerating expansion. Dark energy, as we call it, may simply be the vacuum doing what it's always done, holding structure, humming silently, shaping destiny. But if even the vacuum has energy, and energy has mass, then is empty space heavy? Does nothing weigh something? In a way, yes. The vacuum contributes to the total energy of the universe. It curves space. It adds gravitational influence, and yet it cannot be removed. You cannot scoop it out. It's the baseline, the default, the floor of being. So mass, which feels like an object's attribute, is connected to something far more vast, to a sea of fields and rules and broken symmetries, all layered atop a vacuum that's never quite still. The firmness of a chair, the heaviness of your hand, the presence of your body lying in the quiet of night. All these are echoes of a universe that decided long ago not to remain symmetrical. That decision, that break, is still unfolding. Every atom, every quark, every ounce of mass is a continuation of that moment. And through it, we are able to exist, not as flashes of light or rushing energy, but as things that stay, that rest, that push back. Still, the question lingers. Why did the universe choose to break its symmetry? Why not remain smooth, featureless, massless? What determined the specific way in which the Higgs field tilted? Why does space support this particular set of patterns and not others? We can describe the how. We can model it, test it, simulate it. But the why, the origin, that remains in shadow. Yet perhaps the better question is not why it broke, but what that break allowed. Without it, particles would remain massless, unable to gather, unable to rest. No atoms, no chemistry, no stars, no thought. It was only through imperfection that complexity arose, through asymmetry that stability emerged. So now we return to the idea of mass as permission. Mass is not a gift, nor a possession. It is a result, a reflection of how a particle dances with the fields that cradle it, how it resists, how it responds. Some particles, like photons, never couple with the Higgs field, and so they never stop. Others are bound to it, and their dance is slower, richer, more nuanced. The difference is not one of better or worse. It's a difference of roles. The massless are messengers, swift and pure. The massive are builders, makers of structure. Both are needed. Both define the universe. And you, lying still now, are made of both. Your body, heavy and warm, is mass incarnate. But your senses, your thoughts, your warmth, they are carried by light, by particles that never rest, yet always arrive. The boundary between mass and masslessness lives inside you. So as you drift towards sleep, know that your weight is not a burden. It is a dialogue between fields and space, between symmetry and change, between energy and rest. And this dialogue has been going on since the beginning of time. But then, if mass is so deeply tied to structure, what happens when that structure disappears? What remains when particles decay, when energy escapes, when forms collapse into darkness? When a star dies, something extraordinary happens. Its light, once a constant breath across the dark, begins to fade. The core collapses inward, folding space with it, and in some cases nothing remains but a point, a black hole. No surface, no texture, no light. Just mass compressed beyond comprehension, sealed inside an event horizon. And here, at this threshold, we must ask, where's the mass now? What is it made of if the particles that once carried it are crushed into something unseeable, unreachable? The black hole doesn't reveal its contents. It only shows us its mass, its spin, and its charge. These are the only properties that remain observable. All else, temperature, chemical makeup, even the identity of the matter that formed it, is erased. But the mass endures. It curves space. It pulls at nearby stars. It bends light into circles. It asserts itself. And somehow, that assertion is all the universe needs to keep the accounting balanced. Mass in a black hole no longer comes from dancing particles or vibrating fields within protons. There's no need for the Higgs field to act directly on anything inside the event horizon. The structure has broken down, the forms have disappeared, but the gravitational influence, the mass, remains. This tells us something deep. Mass is more than the sum of parts. It is more than what you can point to. It is more like a footprint, a lasting curve in space, a scar left by something that has vanished. And yet, it also invites another question. If the structure is gone, If the particles are no longer behaving as particles, if no field can be tested inside, then in what sense does mass still exist? The answer, unsettling and elegant, is that mass survives in geometry. It's encoded in the shape of the surrounding space. A black hole could form from collapsing matter, from pure energy, from the crushing of radiation. It doesn't matter. What's left behind is the same kind of curve. The origin disappears, the mass remains. This leads us into the concept of mass as geometry, mass as the fingerprint of energy on the stage of spacetime. Whether it comes from matter, radiation, or field interactions, mass always ends up doing the same thing, warping space, slowing time. And that warping is measurable even from the outside, even if we know nothing of what's inside. That's why black holes can merge. Two invisible centers of mass, each sealed off from the world, can spiral toward one another, losing energy in the form of gravitational waves. These waves ripple through space, like sound through air, not made of matter, not traveling through any substance, but distortions in the fabric of the universe itself. And when the black holes finally collide, their masses don't vanish, they combine. A new black hole forms, with more mass than either had alone, though a small amount is lost to the gravitational waves themselves. That lost energy is gone, but not forgotten. It left behind a measurable imprint, a whisper across space. Even in these extreme events, the rules of mass are obeyed. Mass is conserved, but not in the way we imagined as children. It is not a matter of stuff being moved around. It is energy being reshaped, redistributed, fields being stretched, geometry being rewritten. What we call mass is just the gravitational expression of all these changes. This becomes clearer when we think of systems instead of particles. A proton's mass doesn't reside in its quarks. It comes from their motion, their interactions, their confinement. In the same way, the mass of a galaxy isn't just the sum of its stars. It includes the dark matter holding it together, invisible and unexplained. We see the stars orbiting too fast, the gravitational pull too strong to be accounted for by visible matter. Something unseen is there, something massive. We call it dark matter, but what it is remains a mystery. Still, we can weigh it. We can map its presence by the way it bends light from distant galaxies. We can trace its curves through gravitational lensing, through galaxy clustering, through the motion of stars on the outskirts of spiral arms. It's silent, but unmistakable. So again, mass is not always visible. It does not always come from the particles we know. It can be inferred, so it can be felt. It can be measured in the way space bends. This makes us reconsider the whole idea of substance. If most of a galaxy's mass is invisible, and if even visible mass is mostly the product of motion and tension, then what is the universe made of? Not matter in the old sense, not particles alone, but of energy, of fields, of structure. And mass is the way these things speak to gravity, the way they communicate with space-time, the way they bend and shape and slow, and this reshapes our view of loss. When a star explodes, its light is gone, its form is gone, its elements are scattered, but its mass, transformed into motion, into heat, into gravitational waves, continues. Nothing is wasted. Everything is rearranged. Mass isn't destroyed. It just changes form. Even the mass of you, as you lie here listening, is not one thing. It is a collection. Some comes from the atoms in your bones, some from the motion of those atoms, some from the field interactions within every proton, some from the gravitational binding between your body and the earth. You are held together by invisible forces, and your mass is the whisper of that tension. And when, one day, your body stops moving, when the dance of atoms slows and the heat fades, your mass will not disappear. It will flow outward, past into the air, the ground, the stars. The energy will continue. The gravitational imprint will fade only gradually, blending into the background. You will have changed shape, but not vanished. So perhaps mass is not just about resistance, or inertia, or weight. Perhaps it is a record of the forms that energy once took, of the dance that shaped the structure of space, of the invisible architecture that makes persistence possible. But if all this mass, all this energy, all this structure can be transformed, can be hidden, can be spread so thin that only gravity remembers, then what does it mean to say something truly is? How do we define presence in a universe where everything is constantly changing, yet never entirely lost? Presence. It's a word we rarely question. We assume it's tied to what we can see, or touch, or measure. A rock on the ground, a person in the room, a star in the night sky. If it's there, we say it exists. If it's gone, we say it doesn't. But physics doesn't make such clean distinctions. Presence in the language of the universe is more subtle. It's less about being somewhere and more about how strongly you interact, how much you bend your surroundings, how much resistance you offer to being forgotten. In this way, mass is one of the deepest kinds of presence. It isn't flashy, it doesn't glow, but it shapes the paths of everything near it. It gives the universe its curves. And yet, the more we investigate mass, the more we see it isn't bound to objects in the way we imagined. It hides in motion, in tension, in fields, in the structure of the vacuum itself. It can be disguised as energy, revealed as curvature, or stretched into space so thinly that it becomes a whisper. Nowhere is this more mysterious than in the concept of the vacuum, the quietest possible state of space. No particles, no heat, no movement, and yet not empty. This quantum vacuum is restless, not because particles dart around inside it, but because even nothing cannot be truly nothing. According to the uncertainty principle, the energy of any field in its lowest state is never exactly zero. It fluctuates, and these fluctuations can, under the right conditions, give rise to real particles. This means that what we call empty space has the capacity to produce mass, not from matter, but from potential. It's strange to think that mass might emerge from the hum of a field that isn't even active in the way we normally define it. But we've seen this in the lab. When particles appear out of high-energy collisions, they weren't pulled from hidden boxes. They were coaxed out of the vacuum's underlying possibilities. The energy of the collision, concentrated in one place, gives rise to mass, not by creating something from nothing, but by unfolding a part of the vacuum that was already there, waiting. And because the vacuum has energy, it also exerts pressure. We believe this vacuum energy, this quiet, pervasive baseline, might be what drives the expansion of the universe. Galaxies are not just moving apart, they are accelerating away from one another, not because of force, but because space itself is stretching. This phenomenon, which we call dark energy, behaves as if the vacuum has a repulsive effect, pushing space open. It doesn't come from mass in the traditional sense. It comes from a kind of presence that doesn't cluster, doesn't curve locally, but still changes the shape of the cosmos. This introduces a radical thought that mass and its cousin energy are not only tied to objects, but also to the fabric of space itself. That what we perceive as the presence or absence of matter is just a surface expression of deeper fields, deeper rules. In this view, even a region with no particles, no radiation, no stars, still possesses structure, still possesses influence, still bends the rules. This perspective blurs the line between something and nothing. The void is not void. It is active, potential rich, pregnant with structure. And so mass may not only be a product of interaction, but a sign of hidden order. A signal that the fields of the universe are not flat, but full of shape and memory. Imagine walking across a frozen lake. The ice beneath you looks uniform, but beneath its surface, invisible cracks and stresses ripple outward. Your weight doesn't just rest, it communicates. It finds the grain of the ice, the pressure points, the edges where the structure responds. Mass, in this analogy, is your way of touching the deep rules of the frozen surface, and the lake responds not because of your body alone, but because of the structure beneath your feet. So perhaps mass is the measure of how deeply a particle engages with the architecture of the universe. Not just how much it resists acceleration, but how much it ties itself to the vacuum structure, to the hidden symmetries and broken rules that give rise to form. If that's true, then every mass we measure is also a kind of communication, an expression of the universe's internal language. When you lift a stone, or walk across the floor, or lie down under the weight of your own body, you are interacting with this language. Your resistance to being moved is not just mechanical, it is informational. It is the sum of everything your particles are allowed to be. And the vacuum listens. It listens even when nothing is happening. It listens in the stillness. It carries the memory of every interaction, every ripple, every break in symmetry. That memory is not stored in a book or a record. It is stored in mass, in the quiet resistance of matter to change, in the fact that you don't slip away when no one is watching. So as you rest now, breathing slowly, you are more than weight pressing into a mattress. You are part of a network of fields. You are a ripple held in shape by balance. Your mass is the measure of how tightly your being is woven into the laws of space. But what happens when that weaving becomes too tight? When the curvature of space grows so sharp, so steep, that not even light can escape? What happens when mass compresses itself to the limit, and the vacuum, instead of pushing back, folds inward? When mass collapses in on itself, when it pushes the vacuum beyond its ability to hold it upright, a threshold is crossed. That threshold is the event horizon, the surface of a black hole. It isn't a wall, or a shell, or a crust. It's a place in space where the escape velocity becomes the speed of light. Past that invisible line, and return is impossible. Light cannot climb out. Signals cannot reach us. Time, from the point of view of an outside observer, slows to a crawl. Yet from the falling object's own perspective, time moves forward as always, until the end, until the singularity. If such a thing even exists. A black hole is not a mass in the traditional sense. It has no surface, no structure we can explore. And yet, it possesses mass. That mass determines how the black hole bends space around it, how quickly objects orbit it, how time dilates near its edge. The mass didn't vanish when the star collapsed. It became a kind of pure geometry, a region of space defined entirely by how it curves. And here, mass becomes something abstract, yet terrifyingly real, a number that dictates how strongly space is pulled inward. The more mass, the larger the event horizon. Yet we can never see what's inside. We only know it's there because of the way the outside behaves. Light bends, orbits wobble, waves ripple. The presence of mass is revealed through the structure it imposes on its surroundings. This is a critical insight. Mass does not require visibility to be known. In the end, all we really perceive is how things move in the presence of mass. The stone drops, the planet orbits, the beam of light curves. Mass is not something we touch. It is something we detect through change. And those changes, those distortions, are not random. They follow precise patterns, predicted by Einstein's equations of general relativity. These equations say that mass and energy tell space how to curve, and space tells objects how to move. But this relationship goes deeper than just curvature. Space and time themselves are dynamic. They bend, shift, breathe in response to the presence of mass, the presence of you, your body, your thoughts, your breathing form. All of it contributes a tiny ripple to the shape of the cosmos. Small, almost imperceptible, but it's there. The Earth curves space beneath you. You curve space in return. You are part of the dance. And what's even more surprising is that these curves, these gravitational fields, do not only affect matter, they affect light too. Mass bends light not by pushing it, but by changing the shape of the space through which it moves. This is called gravitational lensing. We've observed it. A distant galaxy appears warped or split into arcs because its light has passed through the distorted region around another invisible mass. We see the image, but we are also seeing the signature of mass we cannot touch. This is how we found dark matter, not by catching it, but by watching its shadow in motion. Galaxies spin too fast at their edges. Their stars should fly away as if loosed from a slingshot, but they don't. They hold together. Something is pulling inward, something with mass. We call it dark matter because it does not shine. It does not reflect. It only curves space. And so mass once again reveals itself through geometry, through motion, through silence. But we've begun to understand that not all mass is created equal. There are two kinds: inertial mass, the resistance to acceleration, and gravitational mass, the strength of a body's gravitational pull. In Newtonian physics, these were assumed to be the same, and every experiment has confirmed it. Push a ball, and it resists based on its inertial mass. Drop it, and it falls with a speed determined by its gravitational mass. And every time, the results agree. This equivalence is what allows us to say that all objects fall at the same rate, regardless of their weight. Yet this harmony is strange. Why should these two seemingly different concepts, resistance to motion and ability to attract, be numerically identical? Why does a thing's reluctance to be moved match precisely its ability to bend space? Einstein placed this mystery at the heart of general relativity. He proposed that they are not just equal, but the same, that mass and gravity are not two forces, but two sides of the same phenomenon, that what we perceive as weight is simply the result of moving along a straight line through a curved space. In other words, you fall not because gravity pulls you, but because the earth has changed the shape of space beneath your feet, and you're following the natural path through it. When you stand still, You're actually accelerating upward because the floor is resisting your desire to follow your natural geodesic, your free fall trajectory through curved space-time. You are not pushing against the Earth. The Earth is pushing against your motion through space and time. Your mass is what causes this path to deviate from flatness. And so, even standing is a kind of defiance. This realization changes everything. It means that mass is not just what makes things heavy, but what gives space its architecture. It is the blueprint for how time flows and how space bends. The presence of mass defines the rhythm of the universe, and yet, the deeper we look, the more mysterious mass becomes. What sets the values? Why does an electron weigh what it does? Why is the top quark so much heavier, while photons have no rest mass at all? We can describe the interactions, but we don't know the origins of the pattern. It's as if the universe were given a set of instructions at birth, and we're only now learning how to read the symbols. You, in your quiet moment now, are carrying these mysteries. Your mass, your structure, your resting breath, they are all echoes of these deeper laws. You feel the downward tug not because the earth calls you, but because space wraps gently around you, holding you in place. You're not fixed, but guided, not pressed, but curved. And perhaps this gentle guidance, this invisible architecture, is what allows time to unfold in a direction we can follow. Perhaps mass isn't just a measure of resistance, but a measure of how the past leads to the future. But then, if mass is so closely tied to the curve of space and the flow of time, what happens to mass where time itself stretches, twists, or breaks? Time stretches most profoundly in the presence of mass. The closer you drift toward a massive body, toward a planet, a star, a black hole, the slower time moves, not in metaphor, but in the very ticking of nature's clock. To an observer far away, your seconds lengthen, your heartbeat slows, your voice would fall deeper, dragged into syrup by gravity's pull on time. This effect is small on Earth, larger on Jupiter, and becomes extreme near the edge of a black hole. There, time does not flow at all from the point of view of the outside world. The clock on your wrist would still tick for you, steadily, but to others it would appear to freeze. This strange warping, this stretch, is not a trick of perspective. It is the shape of time itself being bent by mass. But how can something so ordinary, mass, the thing we attribute to apples and bones and boxes, hold power over time? It returns us to the idea that mass is not simply weight or matter, but curvature, a change in the fabric of reality. Mass doesn't just resist acceleration, it defines the rules by which motion is possible. And motion includes not just movement through space, but progression through time. The more mass in a region, the deeper the gravitational well, and the more slowly time advances within it. This isn't hypothetical. We measure this effect every day. GPS satellites orbiting the Earth must account for time dilation caused by gravity. Their internal clocks tick slightly faster than clocks on the ground because they are farther from Earth's mass. Without correcting for this difference, our navigation systems would become wildly inaccurate. This is not science fiction. This is your phone, your car, your daily reality, quietly shaped by how mass manipulates time. But we can take this idea further. If mass slows time, could time itself be a measure of mass? Could the passage of time in a region reflect the energy contained within it? After all, the more energy a system has, the more it can bend space-time. And since mass is one form of energy, maybe the shape of time in any place is an indirect measure of mass's influence. That would mean that mass is not simply a property of matter, but a sculptor of history. It defines not only how space curves, but how events unfold. This brings us to the notion of the arrow of time, the reason we remember the past, but not the future, why broken glasses don't reassemble, why we age but never grow young. Could mass, or more precisely, the distribution of mass and energy, influence this arrow? Entropy, the measure of disorder, is often invoked here. The universe, we're told, moves from order to disorder, from low entropy to high, and this progression gives time its direction. But entropy depends on how matter is arranged. It depends on the distribution of mass and energy. A box of gas with all the particles clumped in one corner is low in entropy. Spread those particles evenly, and entropy increases. But the rate of that spreading, the way entropy grows, is tied to gravity. Mass pulls things together, creates clumps, forms stars and galaxies. This paradoxically creates local order, even as the total entropy rises. So again, mass becomes a kind of organizer. It structures the cosmos, even as disorder increases. Without mass, the universe would remain a dilute fog of particles and light. With it, we get stars, planets, and observers who ask about time. This strange balance suggests that mass and time are linked not only through physics, but through meaning, through the very possibility of memory, of experience, of story. It makes us wonder, if mass shapes the path through time, and if time shapes the evolution of mass, stars burning out, atoms decaying, black holes evaporating, then perhaps the two are not just partners, but reflections. Perhaps mass is frozen time, and time is flowing mass. The poet might say mass is the frozen music of the universe. The physicist might say it's the scalar response of fields to symmetry breaking. But both are trying to describe the same thing: presence, influence, shape, something that remains, even when everything else passes. And here, once more, mass reveals its paradox. It is both persistent and dynamic. It resists motion, but allows motion to occur. It binds objects together, yet permits their transformation. It slows time, yet enables time to carry on. It is not a thing, but a process, a condition, a relationship. Even decay does not erase it. When particles decay, when atoms split, when radioactive materials emit their energy, mass is not lost. It is transformed. A particle becomes lighter, yes, but the difference in mass becomes kinetic energy, or radiation. The total remains the same. Energy is conserved. Mass is energy. So even in loss, there is continuity. This is why, in particle physics, we do not speak of destruction, only transformation. The top quark decays almost instantly. It doesn't vanish. Its mass becomes the mass and energy of its decay products. Its presence is redistributed. The balance is maintained. In this, we find a kind of reassurance that even at the smallest scales, nothing is truly lost. Mass may change form. It may move or fade or reappear as something else, but its influence persists. You can track it. You can feel it. The rhythm it imposes on the world remains steady. And when we look out into the cosmos, into the great quiet beyond our solar system, we see this rhythm everywhere. The structure of galaxy clusters, the orbit of distant moons, the flicker of light around invisible masses. All of it sings in harmony with the presence of mass. Even the furthest star obeys, and you, here now, resting in your bed, feel it too. You may not notice it in your breath, or your pulse, or your thoughts, but every part of you is shaped by it, held by it. You are not floating in an empty void. You are suspended in a web of relationships, your mass tugging at every atom and being tugged in return. And still, we ask, if mass emerges from fields, and those fields are stitched into the fabric of space, then what is space itself made of? What kind of canvas can hold such intricate threads? We speak often of space as a backdrop, a blank canvas on which matter arranges itself, a volume to be filled, a stage for the play. But in the language of physics, space is not passive. It is not nothing. It bends, it stretches, it fluctuates, it carries energy, it imposes structure, and within it reside the quantum fields that give rise to everything we know. These fields are not sprinkled atop space like paint on a surface. They are part of space itself, encoded into its every point, every angle, every breathless silence. To ask what space is made of, then, is to ask what kind of fabric allows these fields to ripple, and how that fabric itself came into being. Some theories propose that space is not continuous, but granular, that at the tiniest scale imaginable, far smaller than an atom or a proton or a quark, space becomes pixelated, made of discrete units, like the threads in a tapestry. This is the realm of the Planck length, where our usual ideas of geometry break down. At this scale, space may not be smooth. It may shimmer with uncertainty, fuzzed at the edges, never quite still. And this trembling, this foundational flickering, might be what allows fields to exist, to ripple, to create mass. Mass, then, would be not only an interaction with fields, but a response to the grain of space. Like a violin string vibrating in tune with the wood beneath it, particles might acquire mass not just from what they pass through, but from how the underlying structure of space allows them to move. Every field, every interaction, every flicker of inertia could be a whisper from the very foundation of being. Yet we cannot see this structure directly. We cannot look into the Planck scale with any instrument we possess. What we can do is infer its presence by the way space behaves when pushed to its limits. In black holes, in the Big Bang, in the earliest and most intense moments of the universe, space ceases to be a calm stage and becomes something active, reactive, restless. There, mass and energy press so hard against the structure of space-time that it folds, rips, or stretches into new forms. In these moments, mass is no longer just a consequence. It becomes a sculptor. It defines the shape of space, not just in a gentle curve, but in a cascade. It shows us that space is not indestructible. It can be overwhelmed. And when it is, we glimpse the possibility that space itself is emergent, not fundamental, but arising from something deeper. Some theories, about like loop quantum gravity or string theory, propose that space and time arise from even more elemental relationships, tiny loops, vibrating strings, nodes in a vast informational network. In this view, mass might be a resonance, a particular vibration pattern, or a topological twist in a field of deeper rules. And the heaviness you feel when lifting your arm could be the outward expression of a deeper rhythm you cannot perceive, but to which every atom in your body still keeps time. If space is a construction, a fabric born from relationships rather than substance, then mass is a kind of feedback loop. It affects the structure of space, but it is also defined by it. The two are inseparable, like melody and harmony. And this interdependence makes every object, every body, every galaxy a participant in a universe that is not painted onto a canvas, but built into one. This idea is difficult to hold in the mind because we are so used to separating matter from environment, object from emptiness. But there is no emptiness. Even the most distant void between galaxies is full of fields, of energy, of possibility. It resists change. It carries weight. And that resistance, that weight, may not come from what it contains, but from what it is. It makes you wonder, when you lie still and feel the pressure of the bed beneath you, what are you really feeling? Your mass presses down, but it's not a clash of objects. It's an interaction between your body's curvature of space and the Earth's. It's a mutual reshaping of the geometry you inhabit. You are not on space, you are in it, of it, and always bending it ever so slightly. Even your thoughts ride on this architecture. Every signal in your brain, every neuron firing, every flicker of memory or imagination, all of it depends on particles with mass, fields with stability, patterns that endure, and all of that, in turn, depends on the structure of space beneath it. Thought is a movement through mass. Memory is mass in motion. And the persistence of your own consciousness is entangled with the structure of the vacuum, which leads us to a reflection both subtle and humbling, that every idea you've ever had, every choice you've ever made, every dream or ache or comfort has been cradled in a space that bends to your mass, that your existence is not separate from the universe, but a localized event in its ongoing story. A ripple in its field, a curve in its map, and this ripple is measurable. Scientists can weigh your body, your atoms, your particles. They can calculate the energy stored in your chemical bonds, the inertia of your muscles, the gravitational pull you exert on the ground below. But none of this tells the full story, because behind the numbers is a network of interactions, a scaffolding of fields, a stage with its own preferences and rules. So perhaps the right question is not, what is mass made of, but what kind of world allows mass to exist at all? What kind of structure must the universe possess to enable particles to resist acceleration, to form bodies, to persist in time, to fall towards stars to remember? Oh, the answer is still unfolding. It may lie beyond the reach of our current mathematics, or it may be waiting in a new experiment, a new collision, a new whisper from the cosmos. But one thing is certain, mass is not an afterthought. It is not the stuff between the light. It is the condition for pattern, for persistence, for presence. And if presence can emerge from such a strange foundation, what else might the universe be holding in its silence? In the silence of the cosmos, presence takes on many forms. Some are luminous, burning stars, glowing nebulae, radiant arcs of starlight stretched by gravity. Others are invisible, yet more substantial, like the unseen skeleton of the universe. Dark matter. We cannot touch it. We cannot see it. And yet, we know it's there. We feel its presence in the way galaxies spin, in how clusters of galaxies cling together, in the subtle distortions of light across great voids of space. We see its fingerprints, and those fingerprints tell us that most of the mass in the universe is not the mass we know. Ordinary matter, everything we can see, smell, weigh, or burn, accounts for only a small slice of the total. The rest is dark. But what does dark mean here? Not evil, not ominous, just hidden, silent, unemitting. These masses don't shine, don't absorb, don't reflect. They interact gravitationally, bending the paths of stars and light, yet ignore the electromagnetic forces that define our senses. Dark matter floats between galaxies, surrounds them in halos, and moves through ordinary matter like a ghost through fog. And still, it weighs something. It curves space. It holds structure together. Its mass is undeniable. This tells us something profound, that mass can exist without substance, at least in the ways we've traditionally defined it. It can belong to something that doesn't clump, doesn't burn, doesn't decay. We do not know what dark matter is made of. Perhaps it's composed of particles, yet undiscovered, weakly interacting, massive, and stable. Perhaps it's not made of particles at all. Perhaps it's a manifestation of a different field, or a failure in our understanding of gravity. But regardless of its nature, it carries mass, and that mass tells the universe how to behave. We used to think of mass as something obvious, even primitive. Count the atoms, add their weights, and there you have it. But in this quiet revelation, we see mass as something stranger, deeper, a kind of presence that may not be tethered to anything we can break apart or measure directly. A presence that lives in curvature, in motion, in influence. And so we must adjust our thinking. Mass is not the stuff of things. It is a kind of ability, a potential to affect, to resist, to shape. Dark matter affects everything, yet reveals nothing of itself. And still, we rely on its gravity to explain the structure of the universe. Without it, galaxies would fly apart, stars would drift free. The large-scale web of the cosmos, the filaments of matter stretched across the void, would unravel. The very shapes we admire when we look at the night sky owe their existence to something we cannot name. Mass without visibility, gravity without light. And then consider this. If dark matter is invisible and silent, how do we know it's there? Through gravitational lensing. When light from a distant galaxy passes near a massive object, that light bends. The object's mass distorts space itself, causing the light to travel along a curved path. If there's a large clump of dark matter between us and the distant source, we see that bending, even though the matter itself emits nothing. It's like seeing the wind only by the way it shapes the grass. Through this lens, mass is more like influence than identity. We do not need to know what a thing is made of to measure how much mass it has. We only need to observe how it affects the world around it, how it shapes trajectories, slows time, distorts light. And that means mass is not locked inside the object. It radiates in its own silent way, shaping the world without sound. Even within us, there is mystery. Your body, composed of atoms, is mostly empty space. Your atoms are mostly made of protons and neutrons. But if you break those apart, you find quarks, tiny, seemingly point-like particles held together by gluons, the carriers of the strong force. But again, the mass of the quarks accounts for only a sliver of the proton's mass. The rest comes from the kinetic energy of quarks and the binding energy of the gluons. That means your mass, the weight you feel when lying still, is not in the particles themselves, but in the tension, in the movement, in the binding. And so we begin to see a recurring pattern. Mass is not what something is, it's what something does. It's how it moves, how it resists, how it dances with other forces. Even stillness is motion when we look closely enough. Even silence is a hum if we tune our senses to the right vibration. Perhaps that is why dark matter feels familiar in its way. We do not understand it, but we understand the way it behaves. We see it curve space, hold galaxies together, cradle the architecture of the cosmos. And maybe that is enough. Maybe we don't need to see what it is made of to know what it is for. And if that's true, if mass can exist without visibility, without form, then what else might exist, unseen, waiting, whispering its presence through the shape of space? Could there be forms of mass that do not follow even the patterns of dark matter? Forms that hide not just from light, but from gravity itself? Could mass be an emergent property of something even more foundational? And if so, what would that deeper structure feel like if we could lie still and sense it, like warmth through a blanket? There's a theory whispered among physicists that mass itself might not be fundamental, that it could arise from something deeper, something we haven't yet given a proper name. Not just fields, not just curvature, not just the known symmetries of the standard model, but from the information written into the fabric of space-time, a framework in which what we call mass is not a thing at all, but a kind of bookkeeping, a tally of how much influence an entity can exert on its environment, a form of relational identity. Mass not as possession, but as participation. In this view, what we experience as mass might be akin to context. A particle resists motion, not because of its internal heft, but because of its entanglement with the universe's rules, because it's woven into a web of constraints, of permissions and prohibitions, of allowed interactions and forbidden paths. It's not that the particle has mass. It is mass in the sense that its existence depends on a network of interactions that together manifest resistance, gravity, and persistence. Take, for example, the phenomenon of effective mass. In certain materials, like semiconductors or superconductors, electrons don't behave like they do in a vacuum. Their mass seems to change. They respond to forces more sluggishly or more easily, depending on how the surrounding field of atoms influences them. Their inertia is altered not because the electron itself has changed, but because the environment redefines what motion means. The electron's identity is filtered through context, and so its mass, its most defining feature, isn't fixed. This suggests something unsettling, that mass, which we've always considered intrinsic, might actually be emergent, dependent, defined only through interaction. In condensed matter physics, this is not a shocking idea. It's part of the everyday language of how materials behave. But if it's true at small scales, inside crystalline lattices and quantum wells, could it also be true at the scale of the cosmos? Could the mass of a particle depend not just on its Higgs coupling, but on its relationship to the vacuum as a whole, on the shape and symmetry of space, on the properties of fields we haven't yet discovered, on aspects of reality we haven't yet imagined? And what if our own mass, the total of what we are, arises not just from the particles that form us, but from how deeply we are embedded in this network? Your body may be composed of trillions of atoms, but their mass is not locked inside them. It comes from movement, from resistance, from structure, from the fields they traverse, from the histories they carry. You are heavy not because of your content, but because of your participation. This is not a metaphor. It is a shift in worldview. It means that existence itself might be less about possession and more about relationship. Mass becomes the way a thing registers with the universe, its way of asserting, I'm here, I matter, I influence. Even a thought passing silently through the neurons of your brain is bound to this reality. The electrons and ions that signal your memory, your awareness, your sleep, all move with resistance. They possess mass, and that mass arises not from their substance, but from their configuration in fields that grant permission for motion. Your very thoughts are slowed and shaped by this fundamental structure. And this brings us to an odd sort of comfort that everything you feel, everything you are, is not floating alone, but deeply connected. You are not an object in space. You are a shaping of space. Your presence is not limited to your surface. It is registered in how you curve the world around you. When you move your hand, it carries not only momentum, but an echo of the forces that shaped you. The bones in your fingers are forged from stars. The molecules in your skin were sculpted by fields that give mass to particles long before planets had cooled or air had formed. And still, as you lie here, quiet and still, your body participates in that same ongoing conversation. You resist being moved. You slow time around you. You pull infinitesimally on the moon and the stars. You are an influence, not a bystander. This kind of thinking shifts our understanding of permanence. We often think that when something fades, when it vanishes from view or breaks apart, it's gone. But if mass is not located in objects alone, but in the structure of their relationships, then maybe nothing is truly gone. Maybe it's only rearranged, retuned, repositioned within the network. A memory, after all, is not massless. It rides on the activity of neurons. It exists within the architecture of a brain, the layout of proteins and electrical charges. A dream has weight, not on a scale, but in the pattern it leaves behind. Even ideas, though intangible, require mass to emerge. They need a substrate, a vessel with inertia, shape, and persistence. So now we find ourselves in a universe where mass is the quiet foundation of everything we know. It does not dazzle, it does not flash, but it enables, it permits, it gives shape and holds shape. Without it, energy would be restless, always moving at light speed, never forming bonds, never holding together long enough to become stars, or stories, or sleep. And perhaps that's why, when we lie still and feel the heaviness of our body sink into the bed, there's a part of us that feels more than just gravity. We feel placement, anchoring, a dialogue between ourselves and the invisible shape of the world. And yet, there remains one question still floating unanswered. If mass is tied to these hidden structures, to the invisible lattice of reality, then what is the cost of having it? What is the universe paying or giving up in order for mass to exist at all? The cost of mass is not something we see directly, but it is paid in every breath of time, in every folding of space. To give mass is to introduce resistance, to slow things down. It is to prevent motion from being effortless, to make change come at a price. In a universe without mass, light would be the only traveler, fast, constant, and uncontainable. But introduce mass, and you invite structure. You allow things to stay, to rest, to bond. That rest is not free. It bends space, slows clocks, imposes memory on motion. And that imposition has consequences. One of those consequences is energy. Every particle with mass carries rest energy, E equals mc squared. Even when you lie perfectly still, Your body radiates potential, a stored readiness. That energy cannot be erased, only moved, transformed, and when it is released, whether in a falling rock, a running stride, or the fusion of atoms inside a star, it spreads out, reshaping the world around it. The star burns because mass is converted to light. You warm your room because the chemical energy in your muscles, rooted in mass, is turned into heat. Mass is a reservoir that feeds time's unfolding. But this reservoir has limits. In stars, those limits define a life. When the fuel runs low, when hydrogen is spent and fusion halts, the balance tips. Gravity, fed by mass, begins to dominate. The star contracts, heats, explodes, or collapses, depending on how much mass it held. That simple number, its mass, determines its fate. Whether it becomes a white dwarf, a neutron star, or a black hole, whether it glows or vanishes. So mass doesn't just shape motion, it shapes destiny. The outcome of a particle's existence, or a star's, or a human life, is not written only in energy, but in how mass slows and anchors that energy, how it permits form to emerge and resist. Yet for all its influence, mass is a burden on the universe. Literally, it bends space-time. It makes curvature necessary. If everything were massless, the universe would remain perfectly flat, undisturbed. It would expand forever without clumping, without heat, without story. Mass is what broke that symmetry, what introduced complexity, what forced the vacuum to respond. Even the Higgs field, which gives mass to particles, does not do so passively. It sits at a certain energy level, a vacuum expectation value, and this value contributes to the energy of empty space. And because energy curves space, the Higgs field itself has gravitational consequences. So just by existing, just by being the thing that makes mass possible, the Higgs field adds weight to the universe. Not a metaphorical weight, a real one, measurable, gravitational. And that brings us back to the vacuum again. The so-called emptiness of space is not truly empty. It is filled with the residue of fields like Higgs, electromagnetic, and others we may not yet know. Each field contributes a little, like 1,000 quiet instruments playing a background hum, and that hum shapes the expansion of space. Too much energy in the vacuum, and the universe would fly apart too fast for stars to form. Too little, and it would collapse before galaxies could bloom. We exist in a delicate middle. The mass we have, the vacuum we move through, the curvature of space, these are all in balance. A fragile tuning that allows structure to persist. But this balance comes at the cost of uncertainty. We don't know why the Higgs field has the value it does. We don't know why some particles couple to it strongly, gaining mass, while others remain light. We don't know why the vacuum energy isn't catastrophically large. According to quantum theory, the sum of all possible vacuum contributions should be enormous, yet what we measure is small, infinitesimal. This mismatch between expected vacuum energy and observed cosmic expansion is one of the greatest puzzles in physics. A discrepancy so wide, it suggests we're missing something foundational. And yet, here we are, breathing, resting, holding mass, as if the universe knew how to balance the books, even when we don't understand the accounting. So when you lie still and feel the pull of the bed, remember that you are feeling more than gravity. You are feeling a deep agreement, written into the universe long before there were stars. You are feeling the outcome of fields interacting, of symmetries broken, of energy curved into form. The weight of your hand is a story of relationships and permission and constraint. You resist motion because you are part of a world that allows resistance to mean something, to have consequences. And when you let yourself relax into that resistance, when you stop fighting gravity and allow your mass to settle fully into the Earth's gentle curve, you are not losing agency. You are joining the deeper stillness. You are becoming a resting shape in the geometry of space. Your body, your atoms, your particles, each one is now at ease within the structure it helps define. This is the quietest form of being, not to shine, not to fly, not even to think, but simply to weigh, to stay, to curve the world in your shape and let the world curve back. And in this stillness, there are no more questions, just the hum of fields, the curve of time, the resistance of mass, and the peace of being part of something that began long before you and will continue long after.